Savannah Shaw. And Avatar Witcher.
Right.
Anybody I missed? What's your name? What's it? What's your, is that your last name or your first name? Your first name? What's your last name? Did you just sign up recently?
Yeah, actually I did. I signed up like 3 months ago. I went to do photo and I dropped it and I registered back on.
Okay. I will check because you're not on my list, but I haven't got a new list. I mean, this list was from Tuesday, so it might be old. And you weren't here Tuesday, were you? Okay. You get one of these too. All right. I also was informed that the reserve books that I talked about weren't on reserve, but they should be now. The library changed the way they were doing things, so I had to resubmit them. So they should be on reserve now or soon anyway. What's your name? Just give me.
Remind Mitchell.
Okay. Just to let you know. And I guess that's about it. Did everybody get their compass and straight edge? All right. Those that knew about it at least. Okay, last time we finished off talking about angles, right? Oh, we figured out how many degrees in a circle?
360.
360, that came from the Egyptians, okay? And then each degree is equal to what? 60
Arc minutes.
arc minutes. And each arc minute is equal to 60 arc seconds. All right. This also corresponds to how good human eyes are. Everybody's slightly different, but you can see with your naked eye, without a telescope or anything, down to a couple of arc minutes separation. Okay? And we can test that. In astronomy, it's actually easy to test because you look for two stars that are that close together and can your eyes separate them or do they look like one? That determines your ability for your eyes to separate. Now, we do not have the best vision. There are animals that have way better vision, like eagles and hawks and stuff. Their resolution is way higher than ours. I mean, they can see to sub-arc minute resolution. The other thing is, if you split that down to arc seconds, that's about the limit of what you can see with a telescope from the Earth, because you're limited by our atmosphere. Our atmosphere distorts the light as the light goes through the atmosphere, and so you can't really see any better than that with the telescope on the ground. But you get away from that, you put it up in space, and all of a sudden you can see better than that. That's why the Hubble Space Telescope, which is not that big a telescope relatively, it's about 2 meters across diameter, is one of the best telescopes ever just because it's where it's located, it's in space. It can see down to about 1/100th of an arc second. So it can see details that you can't see from Earth no matter how big you make your telescope. Okay, now they're getting around that. They're doing tricky things, like out in Hawaii where they have a lot of the biggest telescopes. They do things like shoot lasers through the air, and then they see how the laser bends, and then they make the telescope bend exactly the opposite to try to take away the atmospheric effect. It's kind of like noise-canceling headphones. Everybody's heard of them, right?
Yes, sir.
Where it actually has a microphone, here's the noise, and that flips the phase of it so that it actually cancels itself out. Works really good with like low noises. Doesn't work real good with high noises, but if you've ever used them, like if you're on an airplane, that low, it can take that out almost completely. The high noise is not as easy. It's harder for it to actually work. But you can do the same thing with light, it's just a lot harder. It's still a wave. All right. So when we measure anything in the sky, we measure it by angles, right?
Mm-hmm.
And how far is your fist across?
10 degrees.
Yeah, from the bottom to the top was about 10 degrees, right?
Yes, sir.
Did everybody go out and check the sun with their pinky? Nobody did. How many times is it supposed to cover it?
3 times.
Yeah, because the sun is about how big?
Half of the arc.
Half a degree, yeah, half a degree, or about 30 arc minutes across, right? And what's the moon?
It's,
Yeah, close to the same. Now it varies. The moon varies because, well, actually all of them varies because we get closer and further away. Nobody goes in circular orbits. And so sometimes they'll say, oh, we're having a super moon. All that means is the moon is a little bit closer to us in its orbit. So it's a little bit bigger. The reality is if nobody told you that, you wouldn't notice it. But the press likes to make a big deal about those kind of things. All right. So back to the celestial sphere. Last time we were talking about when you will go outside and you look at the sky, it's like a dome over your head, right?
yes, sir.
Like a dome going over your head. Remember we had Herb the astronomer in the middle here, hanging out. And on our diagram, we did the cardinal points. And we figured out the Earth rotates which direction, toward the east or towards the west?
It rotates towards the east.
Towards the east, right? Which is why everything rises in the east. It sets in the west. All right, good. And what's the point directly overhead called?
The zenith.
Zenith. Okay. All right. So this celestial sphere was the idea, the terminology, actually came from the ancients as they were trying to understand the sky because it made perfect sense when you think about it, because all the stars, when you go out and watch them, they all move together. The constellations don't change, right? They all move across the sky together. So they imagined that the Earth was like this. It was inside this perfect crystalline sphere, and the stars were embedded on it, and the whole thing spins around us every 24 hours. Made sense to them. Remember, the Earth wasn't moving. Now we know that, oh, all these stars are actual distant glowing blobs of gas, billions of years separating. What's actually spinning is the Earth. They didn't even know these were suns, right? To them, they were just points of light. And so many cultures would imagine all kinds of different things up there, like diamonds because they're really reflective, or bonfires, or something that gave off light. And that's all they could imagine. The Egyptians even thought they were oil lamps up in the sky. So it took a long time to understand what they really were. In fact, that didn't come around until after the Renaissance in about the 1700s. All right, so this idea of the crystal sphere going around us, if we think of it like the ancients did, this whole thing spins around us. And it actually makes that noise. You just have to be on the North Pole and hear it. No, don't write that down. That's not right. I made that up. I think we need some oil on our model here.
Definitely.
But the idea is the globe spins around us. The Earth stays stationary in between. It spins around us. How long does it take to spin around once?
24 hours.
24 hours, right? We talked about the fact that the Earth spins on the axis, and the ends of the axis are the North Pole and South Pole, right?
Mm-hmm.
So if you have your celestial sphere, what does it spin around?
Celestial pole.
Okay, the celestial North Pole and the celestial, and where are they? Yeah, they're directly above the North and South Pole of the Earth, right? Because it's really the Earth that's spinning. So, here we go. Here's our celestial sphere. Wow, I almost made a circle.
Yeah.
All right. So I'm going to put here straight up, straight down. So in here, here's the Earth inside. Here's the North Pole of the Earth, South Pole of the Earth, the equator of the Earth. What's the equator by definition? The what?
It's the hottest place.
It's the, what does equal mean?
It's the halfway point.
Yeah, it splits it in half from where to where?
The north to
North Pole to the South Pole, right? So if we took the North Pole and South Pole, you're going to cut the Earth in half. You're going to cut it right through the equator. So it's exactly in half, right? All right. Good. Now we do the same thing in the sky, except we just project everything outward. So we say, okay, straight above the North Pole of the Earth is the
celestial North Pole.
North Celestial Pole. Straight above the South Pole of the Earth is the
South celestial pole.
South Celestial Pole. And straight above the equator is the Celestial Equator. So far, so good?
Yes.
Okay. What's latitude?
I forgot. I think latitude is
What's longitude?
how long it is.
From top to bottom.
What are those?
The altitude of the pole.
No, but I know where you're going with that. You're not wrong, but that's not the definition of it, right? What is your latitude? Latitude is what? And what's longitude? Guess what? If you get lost in the wilderness, it'd be really good to know your latitude and longitude, right?
It's the degrees from, is it from the North Pole?
Is it?
Oh,
Yeah,
yes,
the
it's
altitude
the
is,
degrees zero. Yes, it's zero.
I can't believe we have a whole class and nobody knows what latitude and longitude. I thought this was like
Latitude
common
is the-
knowledge.
It's a geographic coordinates that from the north to south pole.
Nope, but you're on the right track. They are the geographical coordinates. That was a good word. Look, we're on a ball, right?
Mm-hmm.
Yeah.
So they want to be able to map and position anything on the Earth, right? So we have to have some kind of coordinate system.
Mhm.
You know, in math class, you had an XY grid, right?
Yes, sir.
But on a globe, we got to do it slightly different. So they do it as longitude and latitude. Now, latitude is how many degrees you are away from the
Equator.
equator. It's not from the North or South Pole, it's from the equator. Okay? And so, latitude is
How many degrees from the equator?
how far north or south of the equator.
Is that also like a nine-line comment? Would you use it not? Would you use that for nine-line?
For what?
Nine-line? Maybe not.
I
Yeah.
don't know what you're talking about. Sorry.
Military. Nine-line. Like we would send in not coordinates, I guess, of where we were at. And but we would use degrees. Like it wouldn't be like we're here or like we wouldn't be in Commerce, Texas. It would be at north.
Yeah, that's exactly it.
Okay.
Right. So every position on the Earth has a position how far you are from the equator, right?
Mhm.
Commerce, Texas, right here. How far are we from the equator? Here's the equator. Here we are. Yeah, somebody knows it back there. It's 33 degrees. We're 33 degrees north of the equator. Okay. What's the latitude of the North Pole? 90 degrees north. You got to put north or south on it, otherwise you don't know which way to go, right? So all latitudes have to have a north or south, right? So if I went 90 degrees, I get to the North Pole. Okay? If I go 90 degrees south, I get to the South Pole, right? All right, now notice that everywhere, here's Commerce right here, everywhere on a line parallel to the equator is at 33 degrees north. Guess what? It goes right through Kyoto, Japan. They have the same exact latitude as we do. So how do you know where you are if you only have latitude? Well, you don't. You have to have another coordinate, right?
Yeah.
That coordinate is longitude. What's longitude?
It's how far east or west
west you are from the prime meridian.
And what's the prime meridian?
Mm.
Equator but vertical. The lines are vertical,
Imaginary line, but-
right? So let's say you had a ball and you were spinning the ball on your finger or something like that, right? And you want to count how many times it was spinning. Well, it's hard to count it unless you make a mark, right? You have to make a mark and then you just count how many times the mark goes around. Have to do the same thing on the Earth. So we had to say, okay, there's one point, but we're going to call that 0. We're going to measure everything from that point. Okay, that's the prime meridian. That's why it's called the prime meridian. Okay, and the prime meridian is this one right here. It goes right through there, right down here. It goes right through England, right through technically Greenwich, England. Just spelled Greenwich, but you don't pronounce it that way. It's Greenwich, okay, which is London now. Was its own separate thing, but London's gotten huge from when they did this back in the 1800s. All right, they called that 0. And everybody on the Earth agrees that's 0. Why? Well, back in the 1800s, they had an international conference when they were trying to unify this because, if you remember, a lot of exploration was all done in the 16 and 1700s with countries sending ships all over, and all different countries. England, Spain, Portugal, the Dutch sent out people. Everyone was sending out people exploring, and they had their own coordinate system. It was very complicated. And so they all got together and said, we need to have one system and everybody on the same system. Well, they realized that the British had done the most exploration, especially over here in the South Pacific, where Captain Cook had gone and found all these islands, and had marked them all, and they were all in reference to Greenwich, England. So the easiest thing to do would be use that and then convert everybody else's to that. Made the French really mad, but that's been going on forever, right? So yeah, that was accepted then, mostly because the British had had the best and the most charts at the point, so it was easiest to convert to them. So they were determined to be 0. Okay? And that's the prime meridian. Everything's measured from there. What's the longitude of Commerce, Texas? I'll give you, yeah, here's England. Here's Commerce. About how much of the circle is that? Well, straight across would be 180, right? So over here would be
Negative 95.
95, yeah. Did you say that? I couldn't hear you. Yeah, about 95 degrees. Now some people do positive or negative. We usually just say 95 degrees west of England, right? Because if you're going to England, you go east. You could go the other way, but it'd be a really long trip, right? Here you can fly there in about 6 hours. If you flew this way, it would be about an 18-hour flight. I don't know who would go that way. That'd be great. All right, so we're about 90 degrees, about 1/4 of the way around from England. Okay, but sometimes you're right. They refer to this being east being positive and west being negative, so then we would be negative 95 degrees.
So 33 degrees north and 95 degrees west.
Yeah, but the reality in this class is we don't really care about your longitude. But it's how far east or west of the prime meridian. Why don't we care about it? Because in astronomy, and for the ancient people especially, all they cared about was how the sky looked. The only difference with the stars and what they see in Kyoto, Japan as compared to here is they see it 14 hours earlier than we do. But they see exactly the same amount of sky, same amount of stars. Everything is in relatively the same position. So what really matters is your latitude, not your longitude. Okay? And that matters because we live on a curved Earth. If the Earth was flat, latitude wouldn't matter either, because we'd all see the same. You were just in a different place, right?
Mm-hmm.
See, that proves the flat Earth people are wrong. There's still people out there that believe the Earth is not round. But who knows? All right, so right above the North Pole is the North Celestial Pole. Here's Herb in Commerce, Texas, at a latitude of 35 degrees north. Not 35.
33.
33. Sorry. lived in Georgia before this, and it was 35. That was 17 years ago. I don't know. Maybe one of those brain slip things. All right. Can Herb see the North Celestial Pole?
No.
Yeah.
Let's look at it here. Here's the equator, right? Where's Herb? Well, Herb, I know this is kind of small for you back there. Herb's right here. So that angle is 33 degrees, right? That's the definition of latitude. We're 33 degrees from the equator. And the ground is the horizon, so he can see everything in that half of the sky. He can't see the rest because the earth is in the way. If the earth was perfectly glass and we could see through it, then he'd see the whole celestial sphere. Or all the feet of the people on the other side of the earth. All right. So yes, can he see it? Yeah, if he's here, yes, he can see it. And where is it?
No.
Ah, yeah, North Celestial Pole means it's in the north. That's a good sign.
It's like, oh, it's 33.
It's not like
It's 33.
it is 33 degrees. The angle right here, this angle equals your latitude. What is that angle? Give to me an astronomy definition.
It's the altitude of the North Celestial Pole.
Yes. Remember the term altitude? We talked about this last time. Altitude is how far an object is above the horizon, right?
Oh.
The ground is the horizon. So this angle is the altitude of the North Celestial Pole. And the altitude of the North Celestial Pole always equals your latitude unless you live in the southern hemisphere, then you can't see it. Then you flip it around and it's the angle between the south point on the horizon and the south celestial pole. So the whole thing just essentially does a mirror image when you're in the southern hemisphere. Yeah.
We have Polaris up here. Do they have a counterpart in the southern hemisphere?
No. Currently, there's no star right there. There's just a giant knob in the sky. No, and the North, us having North Star Polaris is just pure luck. We'll talk about that next Tuesday. We'll get to that. Okay? Can Herb see the celestial equator if it really existed? Remember, it's just imaginary. Yeah?
You said altitude always equals your latitude?
The altitude of the
North Celestial Pole.
equals your latitude in the northern hemisphere.
Yes, sir.
Okay? Where's the celestial equator going to be? Yes, you can see it because look, it's right here, and he's on this side, right?
90 degrees from the north
The north
celestial pole.
celestial pole. Good. Does everybody hear that? 90 degrees to the north celestial pole. So I'm going to draw a 90-degree angle. Right here, this is the celestial equator, but the celestial equator is not a point on the sky, is it? It's actually a circle. So if you do it three-dimensionally, it goes like this. Notice it goes from exactly straight east to exactly straight west. Okay? Always. It has to, right? Because if we're spinning around the north, east and west have to be 90 degrees away from that. Okay? All right. Then what is the altitude of the celestial equator? Sorry, I didn't hear you.
57.
57, where did you get that from?
You subtract 90 and 32 from 180
Why?
because it's a straight line.
All right, yeah, he's on the right track. Did anybody get that? How much of a circle is this?
Half a circle.
Half a circle. So half a circle has how many degrees?
180.
180. So all these angles have to add up, these three angles have to add up to 180, right? Well, we know that one and we know that one, so we just have to figure out what's left over. So the easiest way is to say 180 minus these two added together, right? So minus your latitude plus 90 is equal to the altitude of the celestial equator. Or in the case of commerce, we can put in numbers. It's 180 minus 33 plus 90, or 180 minus 157, which is 127, sorry, which is 57 degrees. So this angle for commerce is 33. This angle is 57. All right. Does this make sense? Good, because we're going to make it way more complicated. But before we do that,
Do you mean to write altitude or latitude?
what did I put?
Altitude of feet. Is what the altitude or latitude?
Right here?
No, the altitude or latitude. Is it supposed to be latitude?
Here?
No, I think you're right. Sorry, I'm just confused for a second. I didn't see the other.
I don't see a mistake, but I do make mistakes, so keep on top.
Oh, you're fine.
It's easy when you're writing on the board to write something because you're thinking ahead and you're writing something else.
I just need new glasses.
All right, so to help understand this, what it looks like, we're going to use the planetarium. But they can only take like 11 at a time. So I'm going to split the class right here. And you guys go to the planetarium right now. Mr. Ross is waiting for you. He's going to show you a demonstration for about 20 minutes. You're going to come back, and then you guys are going to go. We're going to swap, okay?
Yes, sir.
Because with COVID, they won't let me take the whole class, and it's too big. So normally, we would just meet in there. All right, what I want you guys to do is get out your compass and straight edge if you have one. If you don't, you need to get one. Okay, well, just pay attention to what we're going to do here.
So I'm borrowing a straight edge.
Well, you can use the edge of that. The reason we say straight edge and not a ruler is because that's what the ancients used. They didn't use a ruler. All right, so I have my own compass, protractor, straight edge. I just have Sasquatch size. I have very large ones, okay? So, what do you do with the compass and straight edge? Well, there's numerous things you can do. We're going to talk about a couple of things. The first thing we're going to talk about is how do you bisect an angle? Okay, what's an angle? We talked about this on Monday. Two rays
Yeah.
that connect at a vertex, right? So just arbitrarily make an angle on your page using your straight edge. Arbitrarily make an angle. All right, so if you want to split that angle into two, what you do is you take your compass, okay? You set it at some distance. It doesn't really matter, but you have to make it stay the same. That's the key, is it can't move. So I set it at a distance here, so I'm going to mark a position the same distance from the vertex. So I put the point on the vertex, and on each ray, I mark a position here so that it's exactly the same distance away from the vertex. Okay? Then I take my compass. I can leave it the same size or I can make it bigger. Doesn't matter as long as again, once I move it, it stays the same after that. Then I move my point of my compass up to that mark I made, and I draw a circle in the center, or a part of an arc. And then I do the same exact thing from the other side. Notice they cross each other. Where they cross, as long as you kept those distances right, is going to be exactly in the middle of the angle, and all I have to draw is a line from the vertex through that mark, and I have bisected an angle. And I split that angle exactly in two. What if you wanted to split an angle into four? Well, guess what? Now you just got two new angles. You just do the whole thing again, and you can split them again, right? So it makes it easy to split into half or a fourth or an eighth or powers of two. You can just keep splitting the angles. It's one of the reasons they like the number 360, because there's a lot of values that go into it, right? Where if you had an odd number, it doesn't split as easily. Okay, you want me to do another one?
I think I missed just the part where you marked it. I might have done it wrong because I did it flat.
Okay, let's do another one. I'm going to do an obtuse angle. What does obtuse mean? Greater than 90, right? Does it work on one like that? Sure. Works on any angle. So I'm going to do an angle something like this. Okay? And we're going to bisect that angle. So step one, what do I do?
Put your thing on the vertex.
Put the thing on the vertex and
Draw 2 points on the lines.
yeah, and the key is the points have to be exactly equal distance from the vertex, right? That's what your compass is doing, is making them exactly equal. So I put it on the vertex, make a mark there, and then make a mark there. Yours actually should be way more accurate than mine because this is kind of sloppy, but you got the idea, right? If you're really careful, you can do a really good job.
I'm just trying to figure out how to work it.
Is it brand new?
Yes.
I took drafting in high school and I was amazed. My teacher was a professional drafter for many years and I was amazed at all the stuff you could do with just a compass.
Yeah, you can do an awful lot. Exactly. That's why if you look at the Masons and stuff like that, their symbol is a compass and a square. You can build temples with that. That's all you really need. All right, what do we do next?
Take one of the points.
Yeah, we're gonna have to go to either point. Now you gotta make sure your compass is far enough separated so you make it to the middle here, right? If I put it too small, it's not gonna work, right? I have to make it big enough so they're gonna intersect. So your arcs are gonna intersect. So put it on the vertex, and then I'm gonna draw my arc. Now I'm gonna come to the other one, draw my arc again. And then where they cross,
Oh, so you did the other mark you did. And draw
yes, the key was I didn't change the compass in between, right? That distance and that distance have to be the same. Don't change your compass while you're moving it over there or you're out of luck.
No, I just didn't realize. I was like, where did the second line come from? That was
Right.
my-
Yeah, do it for both of them.
That makes more sense.
And then, yeah, then all you have to do is draw that line from the vertex through.
Easy to tell.
Through there, and you bisected the angle. The two angles are now equal. All right. Nice, useful technique, right? The other things we know the Egyptians did exceptionally well was they could make a perfect right angle. Perfect 90-degree angle. In fact, the Great Pyramid of Cheops, 793 feet on the side, is perfectly a square to within like less than a half a centimeter. I mean, you can't even do that well nowadays with modern techniques, hardly. They were just that good because they really knew their geometry. So what we want to do is Now that you know how to bisect an angle, I want to know how to make a right angle or a 90-degree angle. Because if you can make one 90-degree angle, you can make 4 90-degree angles, and you can make a square, right? Okay. So, if we have a line, let me do it like this. We have a line. And I want a perfectly perpendicular line at some point there. So right in the middle, just say, I'm going to draw a line perpendicular to that using the compass. I want it to be perfect perpendicular. We're going to do the same thing because a 180-degree line is actually just like a angle of 180 degrees, right? So what we have to do is the same thing we did before. We're going to measure out equal distances from the point that you want the 90-degree angle at. So I want it to be there. So I'm going to put my compass here, vertex at that point, mark one side, and don't change your compass, and mark the other side. Okay? So what I've done is just measured exactly the same distance from the center on both sides. So far, so good? Okay. Then, this one, what you have to do is you have to make your compass bigger. Okay? So you have to make it bigger than it was. But you don't have to make it super big. You just have to make it bigger. And what you're going to do is you go to the point you just made, keep the compass the same size, mark, make an arc above and below that line. Okay? Don't change your compass. Make sure it stays the same. Come over to the other side and do exactly the same thing. The key is don't make your compass change in between there. You have to have the same distances.
Okay, it might just be because I'm using this. And I put it on the point, and it doesn't.
It'll probably work better if you have an actual compass.
Okay. That's why I was wondering, because it's like,
And then notice if you did this right, all three of those should line up. And what you've done is you've created a perpendicular line right through that point. Questions?
So you don't change the compass at all
Well,
for all of it, or?
no, you have to have for first. So remember, you do these first two lines like this and this. Then when you go over here, you can't do it the same because then they won't match up here. You have to make it a little bit bigger.
Okay.
But then after that, don't change it.
Okay.
Okay?
Just wanted to make sure that's right.
Because if you didn't make it any bigger, you would never go up here. You would intersect there, and that's not going to affect anything, right?
Yeah.
Does this make sense? All right. Could you lay out the pyramids for the pharaohs? Then the other trick was they lined them up within a few arc minutes of being perfectly north, south, east, and west. We'll talk about how they did that
you
too.
did right under 3 stars too, right?
Well,
I guess from a certain
that's-
view.
you're talking about the Rhine's belt?
Yeah.
We'll talk about that too. That's kind of debatable. All right. Questions about that? You feel comfortable with using your compass and straight edge? You're going to get a homework assignment using them, but I decided not to do it today because I knew some people wouldn't have it, so you're going to get it on Tuesday. Okay. All right. Let's talk about a couple other things. What if, notice up here I did the celestial sphere for Herb and Commerce, right? What if Herb moved to the North Pole?
It would be straight up. It would actually be straight up.
What would his latitude be?
90 degrees north.
90 degrees north, right? Okay. So Herb moves to the North Pole, hanging out with Santa. Not super accurate, but you get the idea. All right. Actually, it's not very accurate at all. Herb's not even in the center. Okay, Herb's in the center. Which direction's north?
Is
Which one's east?
There is no north
Which one's
or
west?
west, but it's all south.
Yeah, it's a really confusing thing. If you're on the North Pole, technically on the North Pole, right? If I'm standing on the North Pole, I step this way, I'm going south, right? If I go back to the North Pole, if I step this way, I'm still going
So,
south. There's only one direction if you're on the North Pole, it's south. There is no east or west. And north, you really mess up and you say, oh, go north from the North Pole. You can't. There is no north when you're at the North Pole. All right. But where is the North Celestial Pole?
Straight up.
Look,
Zenith.
this angle always equals your latitude, right? The angle between the horizon and the North Celestial Pole equals your latitude. But your latitude is 90 degrees, so for the horizon has to be 90 degrees. So the North Celestial Pole is straight up. That has to be, that's the definition, right? The North Celestial Pole is straight above the North Pole of the Earth. So if you're standing on the North Pole, it has to be straight over your head. So far, so good? What happens, or what happens, where is the celestial equator?
the horizon.
The horizon, right? It's 90 degrees away. So your horizon is also the celestial equator. Okay. Now, if you're watching stars move, how are they going to move if you live on the North Pole?
Around.
Are they going to change altitude?
No.
What's altitude? How high they are, right? Are they going to change?
No.
No. Every star in the sky just goes around like this. And the sun and the moon and the planets, they just go around. Now it depends on what time of the year. They might go up a little bit until they reach a maximum height, and then they go down a little bit, and then pretty soon you don't see them for half the year. But they still just go around. Just go around. Everything just goes around. What's the direction that the stars rise and set if you're in commerce? Okay, but what, do they go straight up? And straight down? Do they go around? No? How would you know what direction they make? They always go parallel to the celestial equator. So if you have the celestial equator, if I have a star here, what it means it's going to make a circle like this, parallel to the celestial equator. It's going to go like this and like this. One down here is going to make a circle like this. Okay? Notice that you get up here, and these are all making circles around the North Celestial Pole, right? So these up here that are close to the North Celestial Pole never go below the horizon, right? They just go around and around and around and around. What do we call those stars? Does everybody know? Yes, they're called circumpolar. These are stars which never set. Meaning, any time of year you go out, you can still see them. They aren't up in a specific season. You can see them any time of year. That's constellations like the Little Dipper, Draco, Cepheus, the ones that are close to the North Celestial Pole. Make sense? Okay. How many of these stars are circumpolar? Do any of them set?
No.
No, so they're all circumpolar. They all just go around and around and around, right? What if we moved Herb to the equator? This is North Pole Herb. Herb at the equator, what would his sky look like? And if we're on the equator, we do have north, south, east, and west. What's your latitude if you're on the equator, by the way?
0.
North or south? Yeah, either one. It's like saying 0 or -0. It's the same thing, right? But you have to put a north or south there because otherwise it's not a latitude if you don't put north or south. Okay, where's the North Celestial Pole? What's he say?
It's on the horizon.
It is. What part of the horizon? Right here. So North Celestial Pole is here. The pole it here, and it has to be, right? Because it's 90 degrees away from that. And how do the stars actually move here? Yeah, which means they all go straight up and straight down.
All of them set.
What's that?
All of them set.
Every single one of them. Yep. They're all up exactly 12 hours and set for exactly 12 hours. Unlike everywhere else. All right, you guys to the planetarium. You guys get out your compass and straight edge. No, you can leave it here. You'll come back in here.
That was about far the coolest thing I've seen on this campus so far.
Good, we're gonna go in there more often too, I hope. I'm trying to make it work. We usually, I like teaching the first. Yeah. All right. I got my giant size, Hulk size compass and straight edge. You got your compass and straight edge? If you don't, you need to get it because you're gonna have a homework on it on Tuesday. I decided not to give it today because I thought some people might not have had it yet. But. All right. What we're going to do is we're gonna do a couple of simple things that you can do with a compass and straight edge, things that the Egyptians did. And the first thing we're going to do is we're going to bisect an angle. What does bisect mean?
Cut it in half.
Yeah, exactly in half, right? Exactly in half. So, to do this, just make an angle on your page, any angle. Remember what the definition of an angle is?
Yes. 360 degrees.
No, that's the measure of degrees.
Oh, yeah, 2 rays and a vertex.
2 rays and a vertex. Yeah, they intersect at the vertex. Good. So I just arbitrarily made an angle. Okay, make it any size you want. Doesn't matter. And we want to split that angle exactly into 2 equal angles. Split it in half. To do this, how many of you did this, have done anything like this before? Did like a geometry class or anything? Okay. Some schools do. I find very few do it nowadays. They used to do a lot more, but schools are reducing what they do. All right, take your compass to bisect the angle. Put it at some arbitrary distance. It doesn't really matter, but what you have to do is whatever angle you make this, the distance you make this, has to be the same as you mark it. So you put the vertex, the point on the vertex, and you mark on one ray, and you mark the exact same distance on the other ray. Okay, so don't change that compass in between. So all we've done is mark points on the rays that are exactly the same distance from the vertex. Then, take your compass. You can leave it the same size. You can change it. It doesn't matter. But again, once you start drawing, you got to make sure it doesn't move. You go to the points you made, put your point right there, and draw an arc in the center of the angle. Then I'm going to pull it up here. I'm going to put it on my other mark and draw an arc in the center of the angle. And you see where they intersect is actually exactly the center of the angle. As long as you didn't change the size, that will be the exact center. And then all I have to do to finish the angle is draw that line. And if you were careful and your compass didn't slip or anything, you perfectly bisected that angle. We messed up. All right, so you mark these 2 points.
Yeah.
When you get to there, I'm going to make it a little bit bigger here. As you put this on here, you draw your arc in here. Like that. And then I go to this one and draw my arc in here. Now, from there through there is the exact same. Does that make sense?
Yeah.
All right, so you see that? Does that make sense?
Yes, sir.
Let's do it again. But now this is a acute angle because people like looking at it because it's less than 90 degrees. Let's do it with an obtuse angle, which means it's greater than 90 degrees, right? So let's redo it, do it again, just to practice here. So I'm going to do an obtuse angle. Okay, some angle bigger than 90 degrees. How are we going to do it? We're going to do the same exact thing. So do exactly the same thing. Set your compass to some distance so that you can mark it on both sides. The same distance from the vertex. So I put the point on the vertex. I mark it on one ray. I mark it on the other ray. Then you move your compass, put the point at the mark you just made on one side, and draw an arc in the center of the angle. Move the vertex point down to the other one, and draw an arc in the center of that angle. I almost didn't make them intersect because I didn't make that one big enough. But I can go back and do it if I don't change, as long as I don't change it, don't change your size, you're okay. And then where those intersect is the center of the angle. And there I go. I just split that angle into two. What if I wanted to split an angle into 4 parts? You just do it again, right? Because now I split it in half. I can split each of those angles into 2 more. If I wanted it 8 pieces, I could split those again, right?
Yes, sir.
Or 16. So powers of 2 work out really good. You just keep splitting and splitting and splitting. Which is one of the reasons that the Egyptians like 360, because there's a lot of factors for it, right? A lot of things you can split it with. So if you had a prime number of things, you couldn't split it into nice even numbers.
So question.
Yeah.
If you wanted to split that left half, right?
Right.
So say, would you put the compass on the other green mark, the 2 green marks that you put in the half, and just make new marks?
No, you gotta make new ones because those are not the same distances.
Okay.
Okay, so what you have to do is you can say, I'm just gonna do the top angle now. I'm gonna put this back here on the vertex, and I'm gonna make new marks. I'm gonna ignore these other ones, okay?
Okay.
And then I go out, oh, I gotta make it shorter here, because I'm gonna run out of board. And I mark those positions. And now if I draw that line, I just split that one in 2.
Okay.
Okay? So yes, you have to make new marks every time.
Gotcha.
Okay? The other thing we want to do with the compass and straight edge is to make a perfect right angle. We want to know how to make a right angle. Why? Because that's what the Egyptians did when they built their pyramids. When they were building the Great Pyramid of Cheops. Each side is about 783 feet long, but it's perfectly square to within a couple of centimeters, which is really good. I mean, that's about as good as we can do today with modern technology. How did they do that? They just used a compass and straight edge, and they were very good at what they did. They had a lot of practice. They built a lot of buildings. Okay, so in this case, just make a line. Make a line kind of in the middle so you got room above and below it. So here's my line. And then I'm going to pick a point somewhere in the middle, doesn't matter where. And I want to construct a perpendicular line exactly at the point so that it makes exactly a right angle using my compass. Well, the reality is I'm doing almost exactly the same thing as I did before, because this is just like an angle, right? It's just an angle of 180 degrees.
Mm-hmm.
So what I'm going to do is put my point on that mark that you want the line to go through and measure out an equal distance on both sides. So make a compass some distance. I'm going to mark it here. And I'm going to mark on the other side so that those are exactly an equal distance away from the center point. So far, so good?
Yes, sir.
Now what do you got to do? Now you got to make your compass a little bit bigger. It doesn't have to be a lot bigger, but it has to be bigger than it was before. And then lock it, make sure it doesn't change, because if it changes while you're doing this, then the whole thing falls apart.
How did you lock the compass?
Depends. Usually yours locks automatically. That's you just screw it slightly differently and it should stay. Okay. Mine, I have a thing, otherwise it falls apart. Depends on how expensive a compass you got. All right, now you go out to the marks you made, put your vertex there, your point, and then you're going to make a arc above and an arc below. Now the key here is don't change your compass. Come over to the other side, don't change the distance, do the same thing, like that. Now the key there was to never change that angle.
Mm-hmm.
Keep that distance the same. Now, all I have to do is draw that line. And if you've done it right, all 3 of those points should connect. And you just created a perfect perpendicular line to the other line. What if I wanted to make a square? Well, a square is just 4 90-degree angles, right? So you just make one corner, and you make another perpendicular at where, like if I wanted it to be this side, I just make another perpendicular at this point. And then from there, I just make another perpendicular, and then we'd hit, and you would make a square. Make sense?
Okay, just so I think I know what you just said.
Okay.
The same way we just made that perpendicular line, we will start from the point, pick a distance, make 2 new marks, and then from those marks, draw in the center,
Right.
and then just keep going that way.
Yep, that's one way. There's an easier way. Because we're making a square, we can take advantage of the fact that all four sides are going to be exactly the same length, right? So I can set this to the length. So let's say this mark right here, which I used before, I want that to be one side of my square, right? So I'm going to make a square like this with all of them being that side. So I know that side has to be that big, so I'm going to mark this. I'm going to measure this and make my compass exactly that side, right? That means that up here, I can make an arc because every point on that line is exactly that distance away, right? And then I go over here and I mark this point. Now this side and this side have to match because those distances match, right? And then I put this one up here and I go like this. And where those cross has to be my other corner. And so there you go. We just made a square. All I have to do is connect these. And I made my perfect square. Mine might be out a little bit. If you're careful, you can make it perfect, all right? My compass is not the highest quality. It tends to be a little sloppy move, and that's not good. Questions about that?
How would they measure the angle?
How would we know it?
How would they?
Well, they would do this and know that that was a perfect 90. They wouldn't use anything like a protractor to actually measure. Okay, but they did know things like the Pythagorean theorem. They knew that a 3, 4, 5 makes a perfect right triangle. So they would have a rope that has knots at exactly the same distance. They said if they make one side 3, one side 4, the other side 5, then you've made it a right angle too. So they had a lot of tricks. But no, did they use a protractor? No. And the pyramid is lined up within a few arc minutes, but that's a lot less than a degree, of being perfectly north, south, east, and west. We're going to talk about how they did that too. You can only do that using the stars.
So if we have like all this technology, why can't we like top the Egyptians right now?
We can. What they use now is if you've seen guys with surveying instruments, yeah, they get it actually very precise with surveying instruments. What I'm talking about is more of your general contractor. If you want to make it precise, we can make it super, super precise. Yes. Oh yeah, we can make it down to billions of inches if we want to. They had to do that with stuff like the LIGO observatory, or it has to be perfect, but most of them, no. If you just hire a guy to build your house, most houses are not perfectly square. They're probably only an inch or two off. But it doesn't really matter, you never know. Okay, but to the Egyptians, this was a big deal. Perfection was important because that's how you get to the afterlife. All right. Questions about, yeah. Okay, you, like I said, you will have a homework doing this on Tuesday. And on the first test, you'll probably have a problem where you need to use your compass and straight edge too. So a little practice always helps. All right, we're gonna go back to here. Notice that, I was talking in the other class, so I have all these lines in here that you didn't see before. We were talking about, and you guys should have seen this. Did Mr. Ross show you this in the planetarium? Did he show the stars moving?
Yeah.
Okay. You notice that, and did he have a setup for commerce?
Yes,
Yes,
sir.
he does, okay. Notice that the stars came up at an angle, right? They set at an angle. What's that angle? It's what? We only have 2 angles up there.
Yeah, that's what it is.
Not 33, try again. 57. You only had 2, you had a 50-50 shot. Why? Because, remember, everything spins around the North Pole, right? The pole is the rotation axis. So all the stars are going to go parallel to the celestial equator. So wherever your celestial equator is, all the stars are going to go parallel to that. So if there's a star down here, it's going to make a path that is parallel to the celestial equator. Rise over here and set over here. There's one over here, it's going to make a path like this, from east to west. And when you're up here, it's going to go a bigger and bigger circle until if you get close to the North Celestial Pole, these just go around and around. They never set, right? Because everything goes around the North Celestial Pole, so they just keep going around. Because we can see the North Celestial Pole, they just make circles. Now it takes 24 hours, so it doesn't happen very fast. These stars up here that never set, we have a special name for them. We call them circumpolar stars. Or if you're Egyptian, they're called the imperishables, which sounds way cooler. Meaning that they never go away. Remember these when we talk about the Egyptian pyramids, because these are the stars that the pharaohs were trying to transport themselves to in their afterlife to rule after they died. They wanted to go north to the imperishable stars. Yes?
Okay, my main question is, because I was looking at how big the universe is, how did we get telescopes to go that far?
You just got to have a big enough telescope.
Is it out the Milky Way galaxy?
Yeah, the key is the bigger the telescope, the fainter the object you can see. Right? So if you get a big enough telescope, you can see really faint objects, or really faint objects are really far away. So really what you're seeing is just fainter and fainter objects. Well, the fainter you see them, the further they are away. And that's why we can see things so far away.
Okay, so are we really seeing the things for how they truly are, or it's just like...
No, you're seeing the way they work. Because remember, it takes light a while to get there. Like the Andromeda Galaxy, we look at it, we're actually seeing the way it was 2 million years ago. Meaning if there was an alien in Andromeda looking at us, there would be no humans. 2 million years ago, we were still apes in Africa. So things happen fast, right? So yeah, you're seeing things in the past. You're not seeing things the way they are.
Yeah, I heard that galaxy is actually moving, like,
Yes.
I don't know.
No, you're right. Our galaxy is actually moving towards Andromeda. We're going to collide in a couple billion years. I'm planning to come back.
I might go to another planet.
It actually won't hurt us. It'll just make our sky really spectacular. But the odds of stars hitting is not going to happen. There's so much space between stars that two galaxies can go right through each other and not a single star will ever hit. Because it's mostly just empty space. But all of a sudden you're, quadrupling the number of stars in the night sky, your sky will look spectacular. So it'd be really cool to see, but yeah. Problem is, how do you hang around for 2 billion years? But working on it. Freeze my head or something.
Maybe by then we might be able to like change the direction of the planets and stuff, so that we won't collide.
With the galaxy? Yeah, I mean, the odds are we're not going to probably run into anything. Okay. But you worry about something colliding with it, like an asteroid running into us. That would be bad. That's what wiped out the dinosaurs 65 million years ago. So, yeah, we don't want that to happen. Then you want to deflect the path of it. And NASA actually is testing that this year. They're going to send a spacecraft out to an asteroid, slam it into the side of it at high speed and see if it changes its orbit. So if we know one's coming, it's like, well, would this actually work? Nobody knows unless we try it. So that's what they're doing. They're testing. All right, back to here. Sorry, I get off track. Back to here. What if Herb lived on the North Pole? What's his latitude?
90.
90 degrees north, right? So it would look like this. Here's Herb. Where's his North Celestial Pole?
90 degrees above him, like a zenith.
Yeah, straight up, right?
Yes, sir.
And where's the celestial equator?
The celestial equator.
The what? The horizon, correct. It's 90 degrees away, right? So the horizon is actually his celestial equator. And which way do the stars move?
West to east.
Yeah, but they always go parallel to the
Equator.
celestial equator, so they're going to go around like this. So how many stars are circumpolar for Herb at the North Pole? Every single one. Where for us, up here, only these. And notice something else. We usually don't draw this part because we can't see it. But the celestial sphere is not half, right? It's actually a full celestial sphere. So if I extend this and make this into a full sphere, and I extend the north celestial pole, what's this point down here?
South celestial pole.
South celestial pole. Okay? And the celestial equator is actually a complete circle. What about these stars down here? They make loops like this. Do they ever come above our horizon? No. We call these stars never visible stars. We're astronomers. We don't go for creativity. These are stars that from commerce we will never ever see. There are constellations down here like the Southern Cross, Alpha and Beta Centauri, some really bright, cool stars, but we can't see them from here. The only way you can see them is you travel south. All right? That's why you travel south, because you go see the better skies. The better skies are seen in the southern hemisphere. If you ever go to the southern hemisphere south of the equator, make sure you go outside and look at the sky. It's way brighter and nicer than it is in the northern hemisphere. There's more bright stars in the southern sky.
I wish I knew this when I went to Peru.
You can go out and look at the sky, that's perfect.
Well, it was a deployment, but.
Oh. Well, they didn't let you like go out and look out.
That's true.
Yeah.
What, I guess you could say, latitude are the, at what latitude south do the large and small magellanic clouds?
You got to get within about 20 degrees.
20 degrees south?
Or north, you get 20 north, yeah. Now, like the Southern Cross and Alpha and Beta Centauri, you can see that from the United States, but only if you're in Hawaii. Or, what's the southernmost point outside of Hawaii? No, further south than that is Florida. If you go down to the Florida Keys, which are the tips of Florida, you can see that. I used to teach in Georgia before I came here. I taught 10 years. And I used to take students on a spring break trip every year. We used to go to the Florida Keys. And our excuse was we were going to see the Southern Cross. The reality is we just wanted to spend a week on the beach. But so what we would do is every October we'd turn the planetarium and the rooms into a spook house, and we'd charge people, and whatever money we got, we used it to go for a spring break trip to Florida Keys. So I've been down there many times, but yeah, our excuse was seeing the Southern Cross, and you can't. It's right above the ocean down there, which is nice because you got a nice horizon. We can see it. We take telescopes and look outside. Mostly we can't. All right, I'll see you on Tuesday. Have a good one. I hope you enjoyed the planetarium.
Yeah, that was
Cool.
Yeah, maybe I'll send it someone. I
You going to
started.
Spinny?
Well, I didn't know I was supposed to do it. They took the lab and everything. So, I don't know.
Oh, I think that's the next stage of TVs. Now we get to ultra high end definition. Well, it's still just in front of you. The key is eventually you want to go immersive where it's around you.
I have a projector in my home, so it's just something that I just gifted, so that's pretty fun.
Nice and big.
Have a good day.
See ya.
You can lock the tunes.
Yeah, I saw you. Okay. Thank you. Yeah, I got you.